Hello, my name is Mark, and in this video I want to present system board for Intel's 8008 CPU. This board allows you to run programs written for 8008 just by sending commands from the PC, without any hassle with reprogramming flash ROMs and stuff. Also, this board provides maximum memory capacity for 8008 without bank switching. And at the end of this video I would compare performance of that 8008 CPU and Intel's first microprocessor 4004, just in very specific task. Let's get started. I want to give brief introduction into 8008 history. Intel 8008 originally was developed as main CPU for data point 2200, and this intention drastically affected its design. But unfortunately CTC released their computer without Intel's chip. Nonetheless, architecture was generic enough to be used in another computers that era. There were such famous kits as Mark 8 and Skelby. Even first portable computer, called MCM70, was based on 8008. You can wonder if 8008 is related to first Intel's CPU, 4004. Truth is that they were developed in parallel, and even more, development of 8008 started earlier. That's why they are very different. From programmer's view, they have totally incompatible instruction set, different amount of registers, and different memory organization concepts. You can tell that Intel 4004 systems follow Harvard-like architecture, with separate storages for instruction and data. But Intel 8008 stores code and data in the same memory space. So, how it works on practice? CPU can address up to 16 KB of memory. It has 7 registers and 2 of them, H and L, are used for memory accesses. If you want to read or to write data to the memory, you have to load target address into that register pair. At the same time, instruction pointer also uses same address space. Memory separation between the ROM and the RAM is on system board's shoulders. It should have logic to determine when address belongs to read-only memory chips. If we are talking about instruction set, it is very limited and has just few basic groups of commands: load instructions, arithmetical and logical operations, some flow control opcodes, and couple of input-output instructions. First two groups of operations can work with registers, immediate values, and values from memory, which are located at address specified by HL register pair. Here is an example of 8008 assembly program that tests RAM. During the first loop, the code writes specific values to the memory, and at the second loop reads data back and checks if it has expected value. Let me explain syntax a bit. First two instructions are load instructions and set values of H and L registers to mediate values, 1 and 0 respectively. Then we write value of H register to the memory location specified by HL register pair, increment value of register L, and write value of L to the memory as well. Registers are 8-bit wide, and if we increment register that keeps number 255, then its value became 0. So we are checking if such overflow happens and if we need to increment high part of the address. CPI instruction compares value of the register A with the immediate value, and if we reach address 4000 in hexadecimal base, then we want to stop writing and start to check the memory content. Verification is straightforward. We are doing the same loop over L and H registers. The LAM command loads data from memory and stores it into register A. Then we have few checks if data is correct, and that's all. Final lines just outputs value of H register into the output device number 8. If there were an error, then H would have some non-zero number. I wrote simple 8008 Toolstack with assembly, emulator and debugger for faster software development. It supports stepping and breakpoints. Also, it displays content of registers and memory. Let's walk through our assembly listening. You can see how H and L registers are changing, and after load operation memory is also updated. We can set breakpoints and check if verification has been successful or not. Okay, looks like memory works as expected. Now we can write and debug programs for target CPU. but we need to design a board with power supply, clock generator, and memory interface to successfully run 8008. Schematic is very simple. PC interface and input power comes from USB connector. Linear voltage regulator provides 3.3 volts for STM32 microcontroller, which is doing all the work. Implements RAM, ROM, clock generator, and interacts with PC. From specification, 8008 works on 5 volt positive supply voltage and -9 negative voltage. But CPU has no ground pin, and we don't care about absolute values of voltages and only need to provide necessary difference in potentials between VCC and VDD, which is 14 volts. That's why I am using step-up switching power supply to generate that voltage. Because MCU and 8008 work on different voltages, we need level shifters in both directions. Signals from 8008 to STM32 are converted with LM339 comparators, and for opposite directions proper level shifting ICs are used. Hardware design was straightforward, and we just need to provide proper signals to 8008. Let's look on timing diagram for the CPU. You can notice two-phase clock and something called states. 8008 is not pipeline CPU, but to execute single instruction it should perform several steps. Instruction cycle is split into several so-called memory cycles. During each memory cycle the CPU reads or writes to data bus. Memory cycle also contains several T-states, and each of such states takes 2 clock periods. I have captured signals from a working system and can illustrate how instruction cycle looks like in terms of signals. 8008 exposes 3 lines that encodes current T-state, which is quite helpful. What is going on during specific states depends on concrete commands, but T1 and T2 states at first memory cycle are always used by CPU to output an address of a next instruction to be executed. You can see that it fetches first byte with value 06 from location 0 at T3 state, and because it is 2-byte instruction, CPU starts new memory cycle and requested second byte from address 1. 06 and 01 encodes instruction to load value 1 to the register A. 8008 performs such operation during T4 and T5 states. First instruction cycle finishes. Next memory cycle is used by CPU to read next instruction, 5.1. It is an output command which sends value from the register A at T1 state on following memory cycle and instruction opcode at T2. Sounds complicated and has a bunch of special cases, but actual firmware is quite basic. Based on datasheet timings, I redrew a diagram with proper scale to determine when I need to read and write data bus. Status lines has a significant drift from actual CPU state. It means that we have less spare time to react. Green line shows moment when 8008 already can start to read the data from the data bus. Luckily, T2 state is always followed by T3, so we can predict memory read from 8008 a bit earlier. Remaining code is trivial. Our memory controller reads data at T1 and T2 states and based on high bits either writes data to internal memory or executes I/O operation. After a couple of sample programs I wanted to run some real code. Of course it was pi calculation. I chose famous Spigot algorithm. There is few good materials about how it works, so I would not stop on that in details. Just briefly mention that idea is that pi digits in special base looks like a bunch of 2's, and we convert number from that base to decimal form. It's not that complex algorithm, but 8008 has no division or even multiplication instructions, so we have to implement multi-byte division and multiplication by our own. After some fiddling around, the program started to return correct data. At first I have computed 255 digits of pi, and it took about an hour. This period is 3 times shorter than the same algorithm which has been run at Intel 4004. So I would say that for some tasks 8008 is faster than first Intel's CPU. Then I have increased number of digits to compute from 255 to 2048, and it took more than 3 days, about 80 hours. Because of memory limitations, we cannot use the same Spigot algorithm for more digits at 4004. But some time ago I wrote a variation for Brice-Billard's algorithm for the successor, Intel's 4040. Calculation of 2048 digits on that CPU took less than 70 hours. 4040 is not that far from 4004. It has no speed improvements except couple more instructions. So obvious conclusion would be that proper choice of algorithm is very important. Thank you for your time, and I hope that this video was at least a bit interesting. You can find all schematics, PCB designs and source code in relevant GitHub repository. I also uploaded my 8008 Toolstack, including online emulator. All links could be found in description. Bye.